Hey YouTube, I'm Dimitri, and we're going to dive right in today. I'm giving a presentation tomorrow up at the University of Texas, Dallas. I'm a presenter for a local chapter of the Global Association for Risk Professionals. I do not represent either of them. I'm just asked as a guest speaker. And so I'm going to do a test, kind of run on my speech here, record it. I'll post it on YouTube probably here like in a week or two. But just going to give it a kind of a run and see how it goes. So let's dive on in. I'm Dimitri Bianco. I'm a risk professional. I've worked at 2 banks and a consulting company where I consulted banks in risk management. And more or less, as I came out of graduate school, I started to see problems with time series models and specifically ARIMA models. So for those of you that don't know, an ARIMA or a ARIMA type model, as I like to call them, is anything that is a autoregressive integrated moving average model. This can be anything from an autoregressive model, a moving average model, an ARMA or an ARIMA, like any combination. I just consider them all as a blanket as a ARIMA type models. And so as I was working in this job, my first job in banking, I started seeing that these models were very unstable. And as I went through my career in banking, I talked to another company, I talked to industry professionals, and I started seeing that this ARIMA structure, the use of time series to model PP&R data specifically, was kind of taboo. Like, people were telling me that, it's unstable, we would never touch ARIMA, and so I'm interviewing for a job at one of these other banks, and they're telling me that it's the worst model that's ever been created. And I'm looking back as my first job, my first experience developing and implementing PP&R models, and I understood kind of this fear. And so as I worked at this first job, I had the academic curiosity. I was not an expert. I haven't been doing this for years, especially at a bank. And so I started wondering, why are these models unstable? And so just to start off with, using ARIMA for everything is wrong, right? There should not be applied to everything blindly. There are a variety of other methods that are available. 2 that I have listed here on the slide is OLS with the Newey-West correction, which corrects for serial correlation and heteroscedasticity problems. Another possible solution for data that's time series related is error corrective models, including vector error corrective models. This is important because you can look at co-integrating relationships between variables. And so just to start off with here in the presentation is we know that you should not force everything into an ARIMA structure. And we're going to kind of come full circle and come back to this at the end of the presentation. And so to start off with, one of the big crucial, points that I saw was that there was a woman I worked with at my first job, and she wasn't well liked by the bank. I met with her at first, and I told her I was a financial engineering background, I'm really interested in time series models, and I'd love to learn more about this ARIMA structure that we're using at the bank. And so I was told by her that more or less I was stupid, I was incompetent because I was a financial engineer. And she was not a financial engineer, she was a PhD in econometrics. And anyways, we kind of had this bumpy start, and I understood why a lot of people in the bank kind of dismissed her. They didn't believe her. They didn't listen to her ideas. They thought she was more or less, somewhat crazy on this. And so I sat down with her, and I kind of came to grips with, okay, you don't think my academic background is very good. You don't believe in more or less the mathematics or the models for financial engineering, and you think econometrics is the end-all, be-all of models. I can swallow that, I can be nice, I can go with it, because I really, really do want to learn why these models are failing. So I put my pride away, and I started working with her. We were working, I think, once a week. She would give me an assignment, I would dive in, I would learn as much as possible, I'd come back, I would show her what I had, and we kept these discussions going about different methods for modeling using kind of OLS, and then moving into co-integrated relationships and seeing why error corrective modeling was important, both from a fundamental perspective of economics as well as from kind of a model perspective. And so one of these key differences is that when you use co-integrated data, one reason to move to this is that more or less data cannot be differenced. And so when you use time series models, it's important for the data to be stationary. If the data is not stationary, it will result in an unstable model. So we at least know that. And most developers will just dive in and start differencing data that is not stationary. However, I found this quite interesting that you could difference data once and make it stationary. Sometimes that didn't work, you differenced it twice. But again, sometimes the differencing I found out didn't really work. Some series just aren't stationary. And one of the interesting parts that I found is I would more or less new to development, I was developing these models, is I would difference the data, and you end up, as you see in this presentation here, with 2 columns using the augmented Dickey-Fuller test. Well, I guess there's a bunch of columns, but the first one gives you the number of lags, and it gives you the row here in the beginning, and that's okay. And then the next 4 columns after that are the p-values for row, the tau, and the p-values for tau. And so I was told as a new developer, that somebody at the bank that was high up, the senior vice president of more or less, some guy that directed the modeling, was told from Dickey himself, who was part of the augmented Dickey-Fuller test, that we were to only look at one of the columns. We were not to look at the other column. It more or less didn't matter what we were doing, but I was told just to look at the one column. And so I asked around different people that were also developers, and they more or less told me the same thing, that this senior person kept telling them, Dickey told us this, we will follow it. So again, I'm looking at this like, well, we have unstable models in the bank, and I want to know why they're unstable. And it doesn't make sense that you're a developer, many of you have PhDs, and you don't understand this. So I wanted to know, and so I spent a lot of time researching, and I came across a paper written by Dickey in 1979 that's mentioned in my paper. And Dickey points out if rho, which is the estimate at the beginning, is greater than 1, you use the tau test. If rho is less than 1, you use the rho test. This seems trivial, this seems stupid, this seems so rudimentary, like something you would just learn in an academic class, something that would just pass through that you would kind of forget, but if you needed it, you could look at your notes and find it. And yet, you have a team of professionals at a variety of banks, they don't understand this. And so the model is not stable. And as you can see in this paper, I actually come across this scenario where if you only rely on one test, the model fails. If you use the other test, the model would pass, being the p-values are significant. And so the question would come up of which one's correct, right? It's wrong just to select one just because you want the model to pass. Like, we need to understand why this is happening. And so I dug into more of the mathematics and the theory, and you can look up Dickey's paper as well. But I at least came to the conclusion I had a solid academic piece that was stating there's a reason, there's a rule of thumb that is used for selecting which test to look at. And so this comes back to a lot of the data, which is that over-differencing can occur, but sometimes sets of data cannot be made stationary. And so this comes back to meeting with this woman that I was meeting with, and she was explaining co-integration. And we spent a lot of time on this. There's a lot of complexities again to time series, and co-integration is one of those kind of concepts where I feel like most of us don't quite get there academically, even with a master's or PhD. And so I spent a lot of time working with her and discussing this. And so co-integration can be used with an error corrective model. It can solve a lot of problems because data, for example, like home prices or home valuations, housing in general during the financial crisis when the housing market popped and values went through the floor, is that the data itself cannot be stationary because you have more or less a stable market. You have some large shift or move in the market that happens very rapidly, very quickly. Or you can have a rebound, or you can have more of a steady kind of like improvement, or kind of a steady like leveling off. But again, the data will move in similar amounts across similar amounts of time. And so since the magnitude in time is similar in both the before and after cases, it's stationary in both those areas. However, this large drop or large spike, whatever you have in your data, will end up causing the data to be non-stationary. And so one might say, Dimitri, what if you, I don't know, bandage this up? What if you just threw out that point? What if you fixed it somehow, right? But this is wrong. This is really, really wrong in time series, and especially in risk management, because we're more or less trying to model those extreme cases. Like, we really don't care, not to say that we don't, but in reality, we don't really care about the good times. We don't really care when life is good, the banks have what they want, they're making money, right? Risk isn't really an issue. It's when that risk is taken on in excessive amounts, especially during those good times, And that leads to these large crashes. And so having co-integration more or less finds that if you have two variables and they can be modeled over time together, if they both show that shift, right, that large movement, they can be co-integrated. So they will move in similar fashions over the same time period. And again, it's important that the residuals of the model are stationary. So the model itself is stable and it doesn't, crash and change over a few different forecasting periods. And so in my paper, I kind of cover these points. Again, I cover them briefly, but I would like to point out in a variety of ways, A, that you shouldn't force models into a structure. If data is not stationary and it cannot be made stationary through a variety of methods, you shouldn't force it. You should look at other methods. Co-integration is a great example. However, there's a variety of different models you can look at. And so that was more or less the issue we had with this over-differencing of data. And so this led me to more or less discover there are other methods, other things we can use that maybe are better than ARIMA in specific scenarios. And so you can see here, actually in slide 5, another problem is that when you over-difference data, it'll start to oscillate. And so you can see here at the partial autocorrelation function, it oscillates. And so this is a key sign you have a problem, you've over-differenced. And so keeping attention to those little details of not over-differencing and reading the right tests and reading them the correct way when you're testing is very important for having a stable ARIMA structure model. And so as I went through again at this bank, or one of the banks I've worked at, I was at a bank and I was sitting down and we had some models that failed. And I was fairly new at this bank at this time. And one of the senior people sat down and asked, he said, Dimitri, you don't talk a lot, which is hard to believe for most of you that know me well. But they asked me, Dimitri, what's wrong? Like, what's your opinion? Why are these models failing? And I just looked at it as kind of a newbie and I said, it looks like you're overfitting. I'm pretty surprised coming from academia, and even when we have class projects, a lot of times they give you some nice, neat data. But being a financial engineer, we typically get market data, and market data is pretty rough to work with. It's not pretty, it's not always stationary, it's not always smooth, it doesn't always make sense. And so it looks like, though, your models are fitting this data very, very well. And so there's this trade-off that we understand in statistics, which is more or less the tighter you fit a model, the better you get it fitting to the data, more or less you sacrifice that great fit for a terrible forecast. And I say that because in reality, we're not modeling reality, we're modeling an approximation to reality. We understand that we can't calculate some behavior in finance. This is not a mathematical calculation, it's not a law. It's more or less just a theory. And so we're modeling people's preferences. And so when I'm looking at this data, I understood it's overfitted. And this came up again as I got a model. I was working on an implementation team, and that model came to my desk, and my boss asked me, Dimitri, this model failed again. Do you think you could redevelop it? I mean, I don't really know if we can or not. I looked at it and I said, yeah, this would be pretty easy to redevelop. I'm sure I could come up with something. And she wanted to know why I was so confident. I told her, I said, just from looking at this model, and you can see on this slide in my paper, I develop a similar model here, that there are too many terms in the model that actually aren't part of the model. And so you have your input variables, and you have your output variable that you're modeling. But this model had one input variable, and then it had 3 AR terms and 2 MA terms. And so the AR and the MA terms are lags of either the variable itself or the error terms. And the problem is these aren't actual variables. These are just more or less adjustments of the variable that you're putting into the model, the input model. And so just from a conceptual standpoint, it seems completely wrong to have a model that is so determined and dictated both by AR and MA terms, as well as the fact that you start learning when you use ARIMA that a lot of times to cancel out an AR term, you can add an MA term. And so when a model has too many AR and MA terms, a lot of times the effects of each are canceling each other out. And so in this model, for example, we had 3 AR terms, we had 2 MA terms. I went back to my desk, I hoped and prayed I was right, and I took out 2 of the AR terms, took out both MA terms, reran the model, recalibrated it, the model fit perfectly, And this was more or less my dream, right? It fits so nice. It was just so perfect. I didn't have to go back and redevelop. I didn't have to look at 100 new variables. Everything was perfect. And so in this paper, I demonstrate a variety of different methods. And so you can see in some of the tables I have the method that I'm using for testing, which is where I develop the model on one set of time series, and then I forecast out 9 quarters. And then I actually trim off a few more quarters of the historical data, and I add it, so now I have a longer forecasting period, and I rerun the same model, but I recalibrate, but I use the same structure. And I do this 3 times. There's a development set with a 9 quarter. There's a kind of a testing set with 12 quarters and one with 16 quarters. And so, and you can see in this presentation here, the p-values are just looking good. I mean, we're all under 1 except for one variable is 0.016, but again, we're way under 0.05, which is our significance level. And then you rerun the same model again, and all of a sudden the p-values blow up on this 12-quarter estimate, and you end up with 2 that are 0.8859 and one that's 0.8999. Anyways, these 2 are more or less canceling each other out. And so what's happening is a lot of times they're actually correlated. And since there's high multicollinearity between these, they will cancel each other out. And when they cancel each other out, it makes the model blow up. But the interesting thing to note, which I don't know if a lot of developers actually notice or have seen, is that when you extend this again and we reuse the same model structure, again, we re-estimate, but instead of 9 quarters where it passes, 12 where it fails, we do 16. And in this time in the 16, you'll notice that the p-values are all great. Again, the model looks perfect. And so this, I think, is somewhat surprising to a lot of people in the fact that the model itself is a crappy model. It's bad. We already know that. We saw that it failed. Especially in financial testing and crises, we don't want it to pass sometimes and then sometimes just fail, right? It seems very unstable. But again, it's because you have this MA and AR term canceling out. And if you read the paper, I develop more or less models that are stable, that don't have these problems based on the methods I use for testing. But you can see in this problem here, the model itself has good white noise in the residuals. So it looks stable. You look at the ACF and the PACF, they're stable as well. So again, this seems from a perspective that it's a very stable model. It's very good. It passes all these tests. But again, a lot of banks and a lot of companies in general aren't testing at different periods. They're not trying to stress the model in different conditions and seeing what actually happens. And when you don't do this, you can miss important stability issues within the model. And this is important both for managers, this is important for oversight committees, because you can catch a mistake by just asking a simple question of, hey, did you guys test this over different periods of time and different forecasts? And they might look at you and say, we've never heard of this. Or, oh, we did it, but we did it over 9 quarters, 10 quarters, and 11 quarters. And you might ask, well, maybe you should do larger periods and kind of see what the results are. And so, again, this is another issue here, is if you're overfitting a model and you're trying to make it look very nice and pretty, and you have this great forecast, and the business area is happy, the developers think they've created the best model that they've ever seen, you end up running into problems. And again, it's just because there's a lack of testing and a lack of understanding that you have to sacrifice the fit for the forecast. And in stress testing, especially with the Federal Reserve here, and CCAR and DFAST here, we really care about the forecast and not as much about the historics. And again, you want it to fit somewhat so we understand that it's modeling the past fairly well and it will help project that onto the future. But again, that forecast is what's important. And again, the details here in the modeling, paying attention to these small details is important. And so we come here into my last point here, which is variable selection. And I'm no genius here. I have a finance background, so I have some business understanding. I've worked in banking. I've worked in consulting for banking. I'm a developer. I'm a financial engineer. I'm an applied economist. I think I'm a pretty smart guy. But one of the key kind of advantages I have when I develop models is I try to understand the problem that I'm modeling before I model it. And I know this sounds like I'm arrogant and it's redundant. However, there's an example where I was given a portfolio to model. It had to do with mortgages. And so the economics department came up with a set of variables they thought were great and perfect, and they gave that to us. And then we had a development team who did cluster analysis, and they looked at a bunch of different combinations, grouped the variables, and they came up with what they thought were, great different variables we should use for this model. And one of the conclusions I kept seeing was that these short-term rates were just really good for the model. And so I looked at it and said, okay, you know, maybe these are perfect, maybe we can build it. But the thing is, I don't really know a lot about this portfolio specifically. And so I went down and I sat with the business owner, well, somebody that worked with the business owners, and they looked at the model, they sat down with me and they said, hey, you know, tell me a little bit about the portfolio, we have this information on it, but for example, can you tell me like how long is a loan? When they originate these loans, how long are these? And also, are these commercial loans, they residential loans? And so they gave me some more information. They told me, you know, it's a commercial loan. It's like 80-something% commercial, but they had to go and actually talk to the business area and get this information for me. And they came back and we sat down and we discussed it. And again, it was commercial. These loans are typically like a medium loan. It was like 10, 15 years was like the average. They gave me like the duration of the portfolio we had. And so I went back and looked at all the variables and I kept looking at it thinking, you know, why are these short-term rates so important? And I thought to myself, I don't really care that these are selected for me by the economist. I don't care that these are selected for me by their developers and analysis. I don't care that these are the ones everyone wants me to use. Deep down, I feel that it's important to stick to the actual facts of what I'm modeling here. And the fact is I should be using longer term rates, something that's hopefully matching this mortgage portfolio. And so this is kind of the key takeaway lesson, which is I used it, the model worked, and it worked for at least a while until I left. But the thing is I don't know if there was a better model, right? We looked at short-term rates. I had some issues with maybe some stability. And so I ended up choosing this longer term because it made more sense from a logical business perspective. And so another example is, again, I sat down with another business owner and they explained to me, you know, interest rate spread. Something that we didn't have as a variable, but something that we could create. And so if you look here at this last kind of example here in my presentation, it's in my paper, is that we try to build a model and we end up with a 5-year rate and a real GDP growth rate. And the problem here is that the model comes out with a p-value of about 0.05 on the 5-year rate. And I tried a variety of variables that we all get from the Fed. I couldn't get a model with a p-value that was less than 0.05. And so I couldn't get this value with a p-value that was less than 0.05. And, you know, I didn't know what to do. And a lot of times in banking and other areas of business, finance, analytics, we need a model and we have to have a model, but we're not quite sure what to do when we can't get one. And so in this case, I've seen a lot of businesses say, you know, 0.0532 is close enough to 0.05, so we can either round it. We could also kind of create tiers, which I've seen people do, which is less than 0.05 is significant, 0.05 to 0.1 is marginally significant, and then greater than 0.1 is insignificant. And since this falls in the medium range, we'll just call it marginally significant, say it's a pretty good model, and move on. And this is something you could do. However, the problem I come down to is that I really want something that's stable. I don't want to risk having this model we have to redevelop year after year. And again, I feel like there's got to be a better solution. And so when I was sitting down talking to a business area expert again, they were telling me that they were using spreads in a lot of their models. And so I looked at them and thought, I've never thought about using a spread. But if the business areas are using spreads for a lot of their analysis, the way they make loans, the way they manage risk, for example, we should also be considering this as a risk management perspective. And so as I'm writing this paper and showing some of the examples of small mistakes that can be made that can result in a really stable model or a really unstable model, I actually came across a spread that I used on this paper, and we end up with a model that's stable. It has 2 actual input variables, no AR and MA terms, and again, we have stability. And so the p-values passed, the model passed. I used my methods of, you know, contracting the historical period and extending the forecast, and everything passes well. And so kind of the take home on the variable selection is just because you have a variable that's like an interest rate or some other type of variable, don't just accept it because it has good correlation or because somebody told you that's what you should use. You should really dig in deep and try to find what is really driving the model and start getting creative. Start looking at different variables that make sense more on a business perspective or an economics perspective that's somewhat outside of the realm of just statistics and modeling. And so for the conclusion here, which again is kind of the purpose of this paper, is it's not to show you that I'm a genius. It's not to prove something new. It's just to show you my experience, right? This journey I've been on, where I've started using ARIMA models, I saw these stability issues. And so I've approached different banks and different managers and talked to people, and a lot of people seem like they didn't really understand why this is happening. And so some banks are just using it because they think it's great and it works. And even though they have stability issues and they're redeveloping every 6 months for stress testing or every annual CCAR practice, they continue to use it because they like it. They think that it works. I can tell you if you're redeveloping every 1 to 2 cycles, it's not working. You're spending a lot of money on development. It's a big waste of time. It's a big waste of money. The bank should really just get rid of you and find someone who's more competent at modeling. But on the other hand, you have people that fear it because they see all these horrible experiences, these examples, the models fail. You go to different conferences and people talk about, oh, I built an ARIMA model and it failed miserably and we had to redo it and it cost all this money. And so then other banks are like nervous and scared. And so the point of this paper is, ARIMA does not fit everything. So don't try to be that guy that's just fitting everything into the ARIMA structure. And I mean, the PPNR is a great example. The Fed's now just throwing their hands there and giving up on modeling PPNR for the most part. And it's extremely disappointing for someone that actually can develop stable PPNR models. But again, not everything fits into the ARIMA structure. And like we mentioned with like co-integration, that's an issue. You can choose simpler models if you don't have issues with serial correlation, or you can use other methods such as the Newey West correction for the estimates. But again, it's just pointing out the little things. And so be careful when you're modeling with ARIMA because you can get really good results if you do it correctly and pay attention to the details. The second point I hope you take away from this presentation is don't follow people blindly. I don't really care if they're like the leading expert in the industry and they just tell you something. You need to find evidence. You need to find proof. So don't just follow people blindly, even if it's an expert in the industry or even if it's your manager or your boss. If it's your manager or boss, sometimes you just have to do what they tell you to do. But you should really be curious. You should really be finding why you're having issues with the model. Or, for example, why are they telling you to do it the way you're doing it? I mean, ask questions. Try to be that person that's going to go above and beyond and be proud of the models you build, but not follow them blindly. And so kind of a famous saying that I always try to live by and try to remember is that never trust reality. Test it, because it never is what it seems. And so in this case, as you can see, a lot of the stability, a lot of the fear that's coming out of ARIMA is because of people are more or less just blindly following people. They're blindly following a model structure. They're not taking the time to really develop something that's true to them, something that's very true to the data. They're not really putting in the time to make a great and stable model. So anyways, thanks for listening to my kind of practice presentation here. Wish me luck, and thanks for watching. And as always, guys, don't forget to share, like, and subscribe. And as always, until next time. Thanks for watching my video. If you find it helpful, please like, share, and subscribe.